So we've got one last lesson in the packet that we're working out of on the second derivative. We're going to cover that today. Wednesday we'll review for the test, and Friday will be test 1. Okay. At the end of the packet that we're working out of, there is a study guide for test 1. So let me just point that out before we start today's lesson. Just flip past all of today's stuff. Class 12 is where we're going to talk about the test, but then right after that, study guide for test 1. So this is page 77. There's a list of things that you need to be able to do for the test, a list of resources to help you prepare, some extra practice problems in the chapter reviews, also old homework assignments, quizzes could be helpful, and then there's a sample test on the next page that starts on the next page. And you can create a 1-page reference sheet to bring with you. You can write anything you want on it, 8.5 by 11. You can use the front and the back. The only stipulation is that you have to create this piece of notes by yourself. Write it or type it yourself. Can't be like cell phone pictures of your notes all made tiny onto 1 page, right? You have to use your hands to write it or type it. Nope, you got to start over, make a new page. You can only use a scientific calculator on the test, so just give you a little bit of warning for that. If you have your own, go ahead and bring it, but I'll also bring some that you can borrow if you don't have your own. All right, so we'll talk more about the test on Wednesday, but I just wanted you to be aware that you have a study guide. And if you log into Moodle, so here are the sample test problems. If you log into Moodle, there are video solutions to all of these sample test problems. So if you're working on these and you get stuck, you can watch the video of either Ian or I solving this problem, each of these problems. All right, so let's jump back to today. All right, so don't forget Project 1's due today. Just put it in your folder before you leave. So today we're going to calculate and interpret second derivatives. So a second derivative is just the derivative of the derivative. Okay? And the third derivative is the derivative of the derivative of the derivative. All right, so for y equals x cubed minus x, I want to find y of 2, y prime of 2, y double prime of 2, and y triple prime of 2. So that's the derivative, the second derivative, and the third derivative, all evaluated at 2. So let's just take the derivatives first before we plug in the 2. So y prime will be just the derivative of x cubed minus x. Great, 3x squared minus 1. And then y double prime will be the derivative of the derivative we just got, which is 6x. And y triple prime is 6. You got it. Now, for each of these, I'm just going to plug in a 2. So I'm going to start with y of 2, which is plug a 2 into the original function. So that'd be 2 cubed minus 2, which is 6. Y prime of 2 means plug a 2 into y prime. 2 squared is 4, times 3 is 12, minus 1 is 11. Y double prime of 2, 6 times 2 is 12. And y triple prime of 2 is what do you get? Yeah, good. All right, so briefly, I'm going to show you how to get some of these numbers on your calculator. Okay. So if you have a TI, if you don't have a TI on Geogebra, it's way simpler than this. You just type in y prime, and first you type in y, and then you just type y prime of 2, enter, and it pops up. Okay. But on the graphing calculator, it's a little bit, and I'll show you on Geogebra in a minute. Okay, so if I want to find y prime of 2 on the calculator, in the home screen, I go to Math, and I choose Nderiv, which is number 8. I type in the function x cubed minus x, and then I have to do comma x, meaning that x is my independent variable. You have to tell the calculator that x is the independent variable. And then you put in a 2 because I want to evaluate it at 2. Now your calculator cannot find formulas for derivatives. It can just find values, numbers, like the slope of the tangent line in one particular spot. So it can find the derivative at 2, but not for every possible x. And it gives me 11.000001 because my calculator is actually doing a numerical method. It's doing f of x plus h minus f of x all over h, and it's choosing a really, really small h. Okay, so it's not always going to give you a perfect answer, but it's a good way to check, your own algebraic work. Okay, so same problem on GeoGebra. Right here. All right, so here's GeoGebra. I'm going to graph my original function, x cubed minus x. Okay, so there's my function. And then GeoGebra named this function f of x, so I'm going to use f as the name now. I want to know f prime of 2, so I just type f prime of 2. And the little prime button is just the apostrophe, and it gives me 11. It's also doing it numerically. It just carries more decimal places than your TI, so it gives you a better estimate. Okay, if you want to see other ways to get your calculator to find derivatives, you can work through this later, right? And this is how you can get your calculator to do try to make it do second derivatives and third derivatives. It will only do first and second. So if you try to make it do a third, it doesn't have the processing capacity. So you can come back to that later if you're interested. All right, notationally, all the primes, like f prime, f double prime, f triple prime, after 3 primes, all those primes start to get a little unwieldy, and you would be counting. That's 1, 2, 3, 4, 5, 6, 7 primes, right? So instead, after 3, we just use a little number. So f, it looks like to the 4th, but that is just a notation for 4 primes. That's the 4th derivative of f. And then you can do d dx notation also. So if you want to take d dx of f of x 4 times, it's d to the 4th over dx to the 4th. All right, so we're now going to introduce a new concept known as concavity. Some of you discussed this with your groups and with me last class because of that interpreting graphs and calculus problem. It had some problems that you were supposed to skip, but we talked about it anyway, which is fine. So we're going to write the intervals of concavity for these 3 graphs. Okay? So if a graph can hold water like a cup, then the function is concave up. And if the graph looks like a frown, then the function is concave down. All right, so this first graph, what do you think? Up everywhere, always up? Yep. So this is concave up on the interval -infinity to infinity, right? It's just always concave up. How about this one? Always concave down. Looks like a frown, right? So this one, if I want to write the interval of concavity, I would say concave down on the interval -infinity to infinity. But then this third one, part of it's concave up. The right half is concave up, and the left half is concave down. Okay? So I'm going to write concave down on, let's see, it's the left half, so -infinity until 0. And then concave up on the interval 0 to infinity. And whether you use a round bracket or a square bracket on the 0 is kind of up to interpretation. Some textbooks will do it differently. So some textbooks will say, it's kind of both, like, because that 0 is the place where it changes from concave down to concave up. So some people would say it's neither, and some people would say it's both, and I won't mark you down however you do it. Okay. Okay, so let's think about how concavity relates to derivatives. Okay, if f prime is positive, then the graph of f is what? We already have talked about this. Increasing, yeah. When the derivative is positive, that means the slope of the tangent lines are positive, and that only happens if f is increasing. Okay, if f prime is negative, then the graph of f is decreasing. Okay, if f double prime is positive, okay, so f double prime is the derivative of the derivative, right? So if f double prime is positive, what's happening to f prime? Not f, but f prime. That's f. What's happening to f prime? If f double prime is positive, f prime is, I heard somebody say it, increasing, right? It's the same rule as up here, right? If f prime is positive, f is increasing. If f double prime is positive, that means that f prime, the function that it's a derivative of, is increasing. All right, so if f prime is increasing, that means that the slopes are getting more and more steep. Okay, so if I have tangent lines that are getting more and more and more steep, what does that do to f? That means f is concave up. Right? All right, if f double prime is negative, that means that f prime is decreasing. Okay, if f double prime is negative, f prime is decreasing. That's the rule from above. So if f prime is decreasing, that means that your slopes are getting less and less steep. Okay, so it might look like a steep one, and then a less steep one, and then a less steep one, right? And that makes a graph of f that is concave down. All right, so these two sentences from number 4 here, memorize them, write them on your note sheet. This will come in handy the whole rest of the semester if you have these two pieces of information in your brain, right? F prime, the derivative being positive means the function is increasing, derivative negative, the function is decreasing. And if the second derivative is positive, the function's concave up. Second derivative is negative, the function is concave down. Okay, so that gives you an opportunity to practice now. Sure.